Thanks for coming to the seminar. We have Greg today. I think most of you would know, except maybe one or two people. Greg was here at UWA, and as you have seen in his bio, in other places as well. And he has been in Sydney after, and now he's back in Paris.
Yes.
I first met Greg at the airport when I first came to Australia. So he was the first person I met in the city. So thanks for agreeing to give the seminar on a short notice, and the floor is yours. And it's all recorded, so we'll have online participants, I believe. We'll find out how many, but we'll get back to this later. Okay, thank you.
So my vocal is okay? Okay, so we've discussed way. The reason I have this for my introduction is because of what I'm going to talk about today. So maybe you get a little help from your friends, but as you're going through life, you can turn left at the blue arrow or right at the red arrow. These are options, right? All through our lives, we make decisions and we take this road or that road, and we don't go back to the other one. So I, a long time ago, started thinking about maybe what we do in economics is not really applicable to these kinds of decisions. How do we take a marginal condition? So anyway, I started out in my life, and you've all started out at different places in your life. I started out my life as a farmer, and then I became an animal scientist. And we all know how scientists are when it comes to economics. We've all tried to work with scientists when we're doing economics. Anyway, there was this thing that they were doing at the time called the least cost gain diet. And I could not convince them that this was complete crap. I mean, it made absolutely no sense. But they thought they were economists, and so this is the way they were going to do it. So I switched and became an ag and resource economist. And there's nobody more devoted than a late convert, right? So I got into my marginal conditions and all of that good stuff. But along about 8 years into this project, I started to have my doubts. So my Diana, who many of you know, and I were going on safari in southern Africa, and we were paddling on the Zambezi above Victoria Falls on the Zambezi River. I thought I was smart. You know, you're from India. Yes. Yeah, I've spent half my life for the last 10 years, and I have some good friends who are also from Kenya, but they're not going back either. Are you going back? Anyway, we were on the Zambezi above Victoria Falls, and I thought I was smart because we were hanging back a bit, you know. The other canoes, if the current starts going, we'll have a bit of warning, and we won't be going over that threshold. What I didn't count on was the hippopotamuses. I didn't know much about them, actually. I knew they liked to chomp people, and I kind of thought they just floated around the pond. That's not what they do. They dive in the water and they run along the bottom, and they're fast. So here comes the hippopotamus. What do? Do I get out my pencil and paper, and I start doing my marginal conditions with my differential calculus to find the marginal benefits of staying just ahead of the hippo versus the marginal cost of paddling? That's not what I did. I panicked. And I survived, and so did Diana. And we got onto the shore, and the guy said, "Well done." And I said, "Well, I shouldn't have paddled so hard. I shouldn't have paddled." He said, "No. The quick and the dead." You were right. Along comes the global financial crisis. Ken Henry, an economist, says, "Go early, go hard." They wasted a whole lot of money. They panicked. They did all kinds of things. But maybe they got it right. I, at the time, was an economist saying, "Oh, come on, you're wasting money. We got to balance this between the cost of the GFC and other costs of messing up the economy." Along comes the pandemic. Now, some economists did the right thing, and they got up and said, we need to measure the marginal benefits of keeping the economy open versus the marginal cost of losing all those old people. And the scientists got up and said, "Shut up. to quicken the dead. It's as simple as that. Now, there were some economists who were also heretics at the time. So Quentin Grafton, everybody here knows, I think, got up and said, to quicken the dead. Tom Combs recently put out a publication, and he basically said, to quicken the dead. Economists really don't have anything to contribute to this, except to agree with the scientists, right? So we don't really have anything to say about turning left or turning right. We are all about business as usual with our marginal conditions. And I really started having my doubts a couple of years ago, a few years ago, 3 years ago, 4 years ago. So I've been into the real options analysis, and there's so many different ways that people are doing this. It's quite a mess. But I thought, okay, we have the Black-Scholes option pricing formula in finance, and it's also used by Dixon and Thunberg and other people in real options analysis. The Black-Scholes option pricing formula has underneath it a stochastic process which just explodes, and I don't think the world looks like that. I don't think it works that way. Why don't we find another way to do option pricing with a stochastic process which doesn't explode? So the simplest one is this thing called the Ornstein-Uhlenbeck process. And I imagined I was Merton, who was the Nobel Prize winner, sitting down with my little equations and doing my kinked terminal value as you do for options, and just guessing and guessing and guessing, till I finally found the answer to an option pricing formula for this thing. And I said, okay, that's wonderful. Now what do I do? And then I was going through my big book of integrals, as you do at the Economist board, I guess. And in this big book of integrals, been there forever, 100 years probably, was this option pricing formula. It had already been done, and it was just a novelty. But they called it something else, and they called it the integral of the cumulative probability. And I said, what is going on here? How can an option pricing formula be a probability? What is going on? So this seminar is about what's going on here. And what I'm going to, probably not convince anybody else, but I'm going to try, is that thresholds are everywhere. They're not an accident. They're not just something that the finance people have made up so they can price the options. They're actually just a fundamental part of life. And everything that is uncertain over time has as one of its fundamental properties a threshold. And that's what gives us these options that we can best to stay this side of the threshold or not. But the scientists are right. Thresholds are everywhere. They're just a fundamental property of life. So that's what I'm going to try to convince you of today. Probably not. I knew Dave was going to be in the audience, and he's always told me for every equation you lose half your audience. So I've kept it to 4 equations, but there's some ones later on. I'll tell you when I'll tell you when this half can leave. But that'll be in a few minutes. Okay? But I'm going to mostly just try to say in words and graphs what this means, and it should be perfectly okay to do that, I hope. So uncertainty over time and thresholds. Option prices and threshold probabilities. Some analytical results, which I'm going to skip over very quickly. And basically just say, what does this mean for us? So the whole idea is to show a few graphs and then say, what does this mean for us? Because I think it means some things for us, if these thresholds really are everywhere, which I think they are. Okay, so I'm going to, another bicycle picture. Yeah, that was it. Wait, yeah. The great thing about this picture, she has a funny front wheel. I don't know what happened.
It's a racing bar.
It's a racing bar.
It's a racing bar wheel. It's a racing bar. She's
on. Oh. There. Okay. They go pretty fast. So uncertainty over time and thresholds. And the subtitle is options aren't optional. There is no life in which you don't have to consider your options. And that has implications for us as economists because we're not very good at this. We're not good at these thresholds. So I'm going to start with a simulation over time, and it's going to be as a Monte Carlo simulation. We're going to start at a particular X. Now this could be, my favorite one right now is temperatures, but X could be prices, it could be utility, it could be anything that you're interested in. And it's going to be subject to random errors, and we're going to simulate it. So X is where we start, Y is going to be the random future variable, and time is going to go on this axis starting from now on up. And as we go further in time, we get a simulation. Okay, so if we do one and we do many and we do all of this, we get a Monte Carlo simulation. And all of these sample paths go around like that. Okay, so people who do options do Monte Carlo simulations a lot, but this actually, as we'll see, doesn't work for that. But what I want to say is that if we want to then decide, okay, what's the chances of this, that, and the other thing, what we do is go out here to some particular time, and some particular y, and we count up all the times something went through there, and we get this probability of actually observing that particular. These probabilities that we're going to come up with are very different from the ones that we used to thinking about. So why is that? Well, it turns out that every observation has its own probability. Okay, so what's a mean? I'm going to step back a couple of steps. What is a mean? Add up a bunch of numbers and divide by n? Well, if we were measuring foot sizes in here, for example, we could measure foot size and divide by n, and that would be the mean. But for things that happen over time, that's not the mean. So what is a mean? We came in, notice the temperature. We're going to leave in a few minutes. What do you expect the temperature to be when we leave? Add up a bunch of numbers and divide by n to calculate this. You say, okay, it was about 15 degrees when I came in, and the sun's going up, and it's going to be 15.5 degrees when I leave in about an hour. What's the temperature going to be after I come back from lunch? A bit hotter. What's the temperature going to be next year? Not too sure.
But I mean, couldn't these still potentially be the mean of the distribution at that point in time?
They are. Each observation has its own mean. Yeah. And each observation
But we're not
depends
talking
upon.
about an observation, we're talking about a prediction or an expectation.
Yes, okay. So you start, we came in and it was 15 degrees. What is it going to be when we go out? Well, we have to factor in how we think the world works, and then we're going to make an expectation of what the temperature will be when we leave. But that depends upon how long it's going to be till we leave and all kinds of things, right?
So I think like get X and Y on the same axis. Sorry, I'm trying to do that.
There. Oh, okay.
It's just a point.
X is just a point where we're starting.
Okay, all right, and everything else is Y.
And
No, Y is the axis.
everything else is Y along here. X is just our starting point.
Okay.
What is a random element?
So you put an x-axis of x0, x index 0.
Y is the random element. It turns out so is X, but that's not the method there. Y is what we think of.
4.5.
Sorry?
Yeah, just treat it as a number, 4.5. Don't.
Yeah. It's 4.5. But now suppose we do this same exercise tomorrow. It's going to be a different X. And we do it in a week's time, it'll be a different X again. So X changes as well. And what I'm trying to say is that every time we make an expectation, we look at where we started, how long we're looking into the future, and our expectations, depending upon how long in the future we're looking and where we started. And every time we form that expectation, it's a mean. And there's no thought of taking a bunch of numbers, adding them up, and dividing by n. Okay, so what's the reason for saying that? Well, every variance is different as well. Every time you make an expectation, there's an error. And every time you make an error, there's a variance. And so every time you observe, there's also a different variance. They're different things. There is a set of assumptions which say that adding up a bunch of numbers and dividing by n gives you the mean. But that requires the world to be in equilibrium every time you observe it. But absolutely no changes. It may vibrate a little bit around some number, but x never changes. Nothing ever changes. Called ergodic, but anyway. We have to throw away our idea of a mean. And we actually have to throw away our idea of probabilities.
Why? I don't understand why you throw it. You just described it as mean. You said it is a mean.
But
the future expectation is a mean of the distribution.
is a mean. But
Or an expected value.
It's a different kind of thing.
But what's going to happen? So we're used to writing down the normal distributions, right? It's got y and u and sigma squared. Our probability distributions are going to have y and x, and time, and many more things in it. And it never actually collapses to our idea of probability.
You haven't convinced me it's anything different to my idea of a probability.
Okay.
Which is not that it's a normal distribution necessarily. It's just some arbitrary ad hoc distribution. I'm sitting here thinking about this as like a decision theorist, right? I've got subjective expectations about distribution of things in the future. Nothing you've said makes me feel uncomfortable yet in that world.
Yeah. Okay, it's just that the probability, the formulas you write down are wrong.
I'm just doing it with discrete distributions, just approximations or which you can make as accurate as you want of the future distribution.
Okay.
I think I'm taking an assumption just based on continuous stuff. It's just static, not based on continuous time. Because I'm just thinking what you're saying, and maybe it makes sense with the meaning about continuous time.
Time is continuous.
Yeah.
And it goes in.
Yeah, but then what you're saying, the definition that we have is normally not based on the concept of continuous time.
The definition we have is based on the concept that time doesn't matter.
Yeah.
And that the whole thing collapses. And it collapses only under these extreme assumptions that the world is always equilibrium. So the usual thing that we see in our statistics books is a special case, but the assumptions to make it a special case are extreme.
This comment to make the assumption we look at the time horizon. I think I would agree with Dave that if you're making a prediction, there's nothing wrong assuming that the stochastic crossing is stationary. So the next period.
Oh well, I'm not going to let you assume that.
Well,
because stochastic processes are never stationary.
Well, you can test whether that's stationary or not.
But yes, I can, and they're never stationary. I mean, they never are. So if you get rid of the stationary, all of our econometrics, it's stationary plus, which becomes ergodic. And nothing's ever stationary. I mean, that assumption is so strange as to be ridiculous. So the finance people don't assume stationarity, and the option pricing people don't either. The econometricians do, but that was invented in the 1930s, about the same time as this idea of probabilities. Okay, you want to assume stationarity.
So in terms of you chart the break, so if I cut at time 4, okay, in reality I'm going to be on any one of those.
Right? On any one of those sample paths, but there'll be a number of sample paths that will go through that point.
Yeah.
You can count those up, and
but by the time I get to t equals 4, I know where I am on that line.
you know that it's t equal 4.
Okay, and then if I take that as a starting point, my new x
Is so
okay.
you might start up there someplace.
Yeah, so are you saying, okay, any of those points on t equals 4 could be starting points?
Yes.
And if I make the tree again,
Yes.
you are saying the trees will look different.
Yes. So every point on there becomes a starting point. As time progresses, we may start here, growing a tree.
So, but for natural process like temperature, why do we have to assume that I couldn't get identical things? Okay, for things like stock markets and so on, maybe okay over time you can't assume things are stationary, but for natural process, whichever and so on, why?
Climate change.
Before climate change.
Oh,
When
but
statistics was made.
okay, but then you have to put deterministic trends in. So it has to be stationary around the deterministic trend. But I'm going to claim that these things never really converge that fast. So I've actually done this for temperatures. And they only become stationary if you wait about 3 weeks. So you have to throw away about 2 to 3 weeks worth of observations for it to actually converge to become close to stationary. So every time it's shocked, it takes a long time to get back. It never actually is back. And then you shock it again before it gets back, so it's just never stationary. It just never has time to converge. If that makes sense?
Okay, I think we should let you continue.
Okay, so we're going to do probability distributions from this. There's a way to go. And you can count up all of those things, or you can write down the formula. And here we start, we have a degenerate probability distribution, which it's all of the probability is right here. But then as time goes, it spreads out a bit. This one is non-stationary. This is geometric Brownian motion. So if you let it run long enough, everything becomes equally unlikely. So anyway, this is a transition density, but every time, I'm now going back into the graph, has a different density. Okay, so this isn't particularly different from anybody else's probability, it's just that we have a lot of this. And if you want to have an expected probability of the future, you think, okay, I want to go 10 years into the future, and this is what my subjective probability might be. Something like that. But depends on how long you look, what your probability that you expect. Okay, so our task is thresholds today. What I want to do is look at this degenerate probability to start out with. And this is the funny thing. It's infinitely narrow and infinitely tall, and the area under it is equal to 1, as all densities should be. It has a name, Dirac density, but it's a funny thing.
Dirac delta.
Sorry?
Dirac delta.
Dirac delta? Yeah. And suppose what I want to do is concentrate on right now, time 0, and integrate it. So let's integrate under here. Well, we've got 0, 0, 0, 0, 0. Suddenly it jumps to 1, and then we add no more to it. So what we do when we integrate this thing is it goes nowhere, then it jumps to 1, and along the top it goes to 1 again. So this is the probability, the cumulative probability of this degenerate Dirac delta. Heaviside function is the step function. Okay, so this is an important thing in option pricing because it's like a switch. It's either off or on, and when we do option pricing, there's these switches running around. If you're happy with Black-Scholes formula, there's these things that switch it on and off. Okay, we got that by integrating like this, and we can integrate the rest of it as well, and end up with a transition probability, which is similar to what we would see, nothing particularly different, except there's a lot of them. It happens in this particular case, only to converge to that horizontal line. That's not the important part. But what does this say, and what doesn't it say? What it doesn't say is that this variable was always less than x. So here's one of those sample paths. And sometimes it's bigger than x, and sometimes it's less than an x. And it crosses back and forth many times. So the probabilities, cumulative probabilities we're used to, we say, okay, we want everything less than y, less than this number. We know for sure that everything was less than y. So if we measure all the foot sizes and we come up with an average of what, and we say how many are less than that and how many are greater than that, we know that everything is less than that when we don't have time in it. But here, this random variable can cross or not cross or go back and forth.
But at a certain point in time, it's greater than or less than y.
At a certain point in time, it's less than, but at a previous point in time, it might have been greater than. Okay. And at a future point in time, it might be greater than or less than it could be. Sure. So we cannot rule out the possibility that it was always, okay, we're measuring all of the things that are less than y, maybe we're here, but we can't rule out the possibility that it's already crossed it.
Isn't that okay unless we assume x is the mean? Because if x could be much bigger than the mean, smaller than the mean. So if that's the case, then it will tend to be on one side most of the time.
Well, I'm going to put one here. It's not going to be anything related to the mean. Sometimes it's bigger, sometimes it's less. Yeah. So what I'm trying to say is that this probability doesn't behave like the probabilities we used to. Just because we counted up everything that's less than y at a particular time doesn't mean it always was. So if you're trying to think that somebody's adopted something, that's why it crossed the threshold. Well, maybe they crossed it and come back and they've done things. It just behaves very differently.
It's not feeling it's behaving differently. It just feels like you're being specific about time, which you have to do when you specify a probability anyway. You have to be clear about what you mean by it.
You have to put time in the formula.
Yeah. I'm not even having a formula. I'm just saying at a certain point in time, there is a probability distribution of our variable. And the key thing is that you're specific about that you're saying at the time that you're talking about, or the time range you're talking about.
Yeah, I'm happy with that. I'm just saying that when we open our statistics textbook, we don't do that. And all of the formal machinery we have to deal with probabilities doesn't do it.
That's where you and I use different formal machinery.
Okay.
Sets, I think.
Oh yeah, there are actually two threads to this. So
it seems to me the difference is that it's a static setting and that's a dynamic setting. That's really what the difference is.
I'm not saying it's a static setting.
No, he's just saying that you can specify any probability you want as long as it's explicit about what it is at some time, and you're very explicit about what the time is.
Yeah.
So I think we're saying the same thing. The difference between me and you is I'm putting time in my formula. I think that's the difference. I'm actually putting it in.
That's what I think.
And
You're trying to explicitly model things through time.
Yeah. And just to put time in the formula.
You have to tell us what the advantage is.
You get different answers. Talk with time in the formula, you actually crank the handle and get the wrong answer.
Certain types of problems. It's probably horses for horses.
Yeah, I don't know. We'd have to check out all the certain kinds of problems. But suppose we wanted to ask the question, what if it was always less than some threshold, k? What we have to do is a different kind of simulation in which we just stop the simulation and don't let anything become bigger than this. So it's a different Monte Carlo simulation. The option pricing people do this all the time. They just truncate the simulation and don't do anything that could be greater than it. And then they count up what's in here to get their probabilities. Now, I'm going to say that is a different kind of thing that we don't usually do. And what I'm going to do is take this step function and integrate it one more time. And so what we're going to do is follow along each of these sample paths that we're simulating and throw out all of the variables all of the times when it's greater than my threshold. I'm just going to do that analytically by integrating this step. Okay, so I'm adding up all of the area, nothing, nothing, nothing. Suddenly it goes to 1 and then stays there. And so I'm integrating under this. Suppose I come out here to 5.5. I've got a rectangle that's 1 wide and 1 tall. And the area under that is equal to 1. Suppose I come out to 6.5. Got a rectangle that's 2 wide and 1 tall. I've got an area equal to 2. And on. So if I integrate under this, what I end up with is 0, 0, 0. And then if y is 5.5, I get y minus x 1 times 1 or 1, or y minus x. And the whole thing integrated just becomes 0 and then y minus x. Okay, so this is option pricing. It's looking like a threshold from an option price. It's got that key threshold. And it comes about from the probability side of things, rather than the way option pricing people did it, which is to just not do probabilities at all. So I used to think we didn't even need probabilities in our lives. Changed my mind. I thought, oh, we can do everything we need to do with just expected values because we maximize expected values and things. So why do we even bother with probabilities? But I'm kind of thinking maybe they are useful. Okay, so here is something that I'm going to call the threshold probability, for lack of a better name. They're different ones, and as time goes on, it would eventually curve to that. It would eventually converge to that.
What sense is it a probability? Sorry for interrupting.
I'm not sure if it really is. I'm giving it that name. It is. It came from the probability previously. I integrated that probability, and now it's much bigger than 1. Like it goes to infinity, right? Which probabilities are all supposed to add up to 1.
What are you interested in having a normalizing factor in front of it?
Except the normalizing factor is going to be infinity. So I don't know. I don't really know what this thing is, but it comes about from integrating those probabilities, and you end up with this kinked terminal value. That's the main point. Maybe it's not a probability. Maybe it needs a different name. But there is a problem here now. So uncertainty over time comes in 2 flavors, or 2 sides of the same coin. There's the kind where we're starting from today and we're looking into the future, and we're coming up with David's probability that we're expecting sometime in the future. And the future is less certain than the present, because the present we know. So we know exactly what the temperature is outside, but we don't know what it might be in a month's time. That's not the way we actually solve our decision problems. So the reverse side of that is, suppose we're here today and we're going to go towards the future, and then the future is going to be something. It may be this threshold, for example. And as the future progresses, we learn where we're going to be on that threshold. So maybe there's a big tipping point for climate change. I'm not quite sure which side of that we're going to be on, but as time goes along, we become more and more certain where we're going to be on that threshold. So uncertainty over time has 2 sorts. This I would call a an initial problem, initial value problem, in which you start here and go into the future. But the other one, where the dynamic optimization is a terminal value problem, where here we are today and we're not really sure where we're going to be in the future, but we'll find out when time comes. Those are two almost completely they seem incompatible, but they're both two sides of the same problem. So what I want to do is flip this into an option pricing idea, because in option pricing, here we are today, and we're going to find out in the future where we are. So if I'm doing a financial option, I'll find out whether my options are any good or not sometime in the future. If I'm doing real options, which is basically everything else, I'm starting from today, and then I'm trying to avoid thresholds that I don't want to cross. I'm trying to cross thresholds I do want to cross. Those are all going to be revealed in the future. So how do I do that? Well, I just basically run time backwards, or do it backwards. So I'm going to make a graph that's now covered up by a few people, but I'm going to. Sorry?
We could move that thing off the screen.
That's all right. It's got Q up at the top, and then it's got 0 to 9.
The little, because of that, that's right.
Oh, okay. So we're now going to think about me not really sure where I'm going to end up in the future, and the future's going to be revealed as I come onto it. This one starts here. This is just this particular formula does this, but I have no real idea where I'm going to be now. It's just a flat line. But as time progresses, it takes some shape, and it converges to that kinked terminal back here. And it's the flip side of that probability. That's weird. Steve is scowling. How did that come about? Well, if I want to do the other, now I'm integrating the other way. I'm integrating, and so I go back. This is like a put option in finance, or an exit option in real options, where you get out of business, or things are not going your way and you just have to sell up and go away. Or in finance, it's like a put option where you have the right to sell. When the price goes down, you still have the right to sell and keep from making losses along this side. But if you want a call option, you just do it the other way. You integrate these probabilities the other way. So now I'm integrating and finding everything that's greater than. And this is the transition probability, and this is the call option. Okay, so my main point is that you can put kinked terminal values into your calculation by integrating these probabilities. And it's an automatic way to find an option pricing formula. But more than that, all of these probabilities have a kink in them if you integrate them enough, and it's a fundamental property of probabilities. In other words, these thresholds and tipping points are everywhere. They're just part of life. That's my main point. Okay, so I guess we start about here. Everybody, I got 4 equations, so it's going to be down to a tackle. Here's my first equation. So we just start with the density, perhaps. We can integrate it and become this transition probability, like we did in the graphs.
So what's S in there?
Okay, so S is today,
Starting time.
right now, today, starting time. X is the starting state of the world, so S is now and X is the temperature right now. T is how long into the future we want to look, and Y is what we need to form an expectation about. We don't know why, but it's going to be that.
So where the temperature will be at T.
Yeah, where the temperature will be at T.
So Y is to X or T is to S.
Yes. Y is to, okay, Y happens at T. Okay, we're making it.
X happens at S.
X happens at S. And what we do to get transition probability is just integrate with respect to Y, like we do for probability. And that's okay. And then this last thing that I did is to integrate it one more time.
So the second equation.
Yeah.
You are integrating over all the values of what you expect the value to be.
Yes.
From minus infinity to 1.
Yes.
Okay, so what the intuition of that, so isn't that the probability that y would be, the terminal value would be y or less, or am I missing something?
Okay, so
How is it equal to y at time t if you are integrating up to y?
okay, so this is all of, we're counting every observation that was less than y at time t. So the top one is everything that actually is y at time t.
Yeah.
This one is everything that was less than y at time t.
Okay, up to y.
Up to y. So
The
minus
first one is the
infinity up to
PDF,
y.
the second one is the CDF. Is that the interpretation?
Sorry?
So the first one is the real probability density. The second one is the cumulative.
Yes.
Up to y. The PDF.
Yeah.
No,
The
the
CDF.
CDF. The CDF. Okay.
Yep. And the only difference between any other one is it has x and s and t in it. So usually our PDFs only have y. So I'm just putting those variables in.
So the second integration is for what?
Then the second integration is what I showed on the graph where you integrate one more time and you get the kink terminal value. And I call this the threshold probability. It's a way to get a kink terminal value in your calculations for one thing. But turns out, you can integrate this two different ways. You can just integrate it, which can be easier or hard, or you can do integration by parts. I have some examples which I won't show you unless you really ask about Black-Scholes option pricing and other things which actually do this. But essentially, we're just integrating again somewhere or another, and it's an analytical way of putting a kink into your calculation and getting an option price. So it turns out the option price is just replace the variables in this thing, and in option pricing, we usually start now. T is now today, and X is where we're starting. And we're going some future big time T, the option pricing people put that in. And we have some kink point, some threshold K. And it turns out that an analytical option pricing formula is just that. So if you can do probabilities, you can do option pricing. I think the reverse is also true. If you're doing option pricing, you're actually doing probabilities. I think the people in finance who think they're just using martingales are probably wrong because they're actually making all of the assumptions for probabilities to exist.
So if you want to explain what the second integration is about?
This one?
Yeah, just in words.
In words.
The other one is the cumulative, which is the probability y, the probability y is equal to y or less. The second one.
Can I use a graph? Okay, so what I'm doing is simulating, but I'm throwing away. I go along this sample path and it starts to go greater than my threshold. I stop there.
Okay. Yeah.
So as I'm integrating that second time, I'm going along each sample path and stopping when it gets to 1. I'm throwing away all of these things that might have crossed this threshold.
Just clarify, what is the meaning of you throwing away everything that's above the threshold?
That's what the option pricing people do. But it's also the idea that we want to make sure that everything was always less than 1. We haven't crossed this threshold. We don't want to have crossed this threshold. The previous cumulative probability, I could have crossed the threshold many times like that. But I don't want to have crossed that threshold. It really is a threshold, and once I cross it, life is different. So the virus hits WA big time, and life will be different. You cross the threshold.
So am I right in understanding that this second layer is about one way you can you're looking at all the possibilities of what that threshold might be, and whatever it is, you're going to interpret underneath it. Is that correct? That's sort of answering the question that faculty asked.
Okay, so So K is just the number of.
But you're integrating vertically and then you integrate horizontally. That's one way of putting it.
We're integrating horizontally with Y only.
And what about the distribution of the X, which is also random variable?
It is. And this without formulas, but X is also a random variable, as in next year, as Atakali said, X will be here. We do this whole process again.
So my question is that second layer, that's round P, does that take into account the fact that X is random?
Yes, they all do that. Yeah, so these, X, it's quite weird, but X is actually a random variable. Even though it's the point we start at. The point we start at tomorrow is a different point. And we don't know where we're going to start tomorrow.
It's not a random variable today, it's an observed number today.
It's an observed number tomorrow.
Today.
But tomorrow it'll be something else. And so it changes randomly between today and tomorrow. So we think the temperature is going to be 16.5 degrees when we go out of here. We observed it's 16.4. We made it in. But now our new starting point is going to be 16.4.
So could we also interpret this by saying that the probability distribution of the Y is actually conditional on X? And so in a way, maybe that third layer is a conditional probability on the second layer.
You could call these all conditional. So Y is conditioned on S, X, and T if you want to. Where we start, and how far in the future we're going to go, you could say that. So you could put a vertical line here between T and Y, and
That's my understanding so far. In terms of these equations, X, S, and X are not random. They're taken at this point. If you try to predict what's the Y in time T, X and S are given at this point. If you talk about tomorrow, you have a different set of S and X. But in this context, S and X is not random.
yeah. So
It's given.
that's exactly right. Right now we know what they are.
So saying that X is a random variable, it depends on how you define what X is. If you say that X is the temperature now, then it's not random. If you say that X is the temperature at some future time, then it is.
Well, X is our starting point, but it's going to be a different starting point tomorrow. So both Y and X actually vary by this stochastic differential equation. Both very stochastic over time. But right now we observe it.
So for tomorrow, the probability that temperature low equal to 18 or less, that's the second one.
Yeah.
Let's say that's 0.7.
Okay.
I am trying to understand the next one. So what am I doing in the next one? Do any of those equations make it easier for me to understand? So let's say the first. So it looks like you are integrating over the cumulative distributions again,
Yes.
right?
One more time.
Yeah, I'm trying to get the intuition of that. So
Good. If you get
so
it,
the last one, the last equation. Now I am multiplying my 18 degrees, okay, by the probability which was 0.7, and then subtracting something. I can't understand that something.
Oh, this? Okay, so is this one okay?
That one is okay. Up to 2, I am okay.
First one and second one.
So all I'm doing here is integrating by parts.
But why am I integrating
Yeah, but why?
the cumulative distributions? Am I accounting for the fact that there are different starting points, so there are different distributions that I have to cover? Why am I? Is that what's happening?
All this is a particular way that you can evaluate this in the
That
program.
one. Okay.
And this is the way that you have to use to get most option pricing formulas because this one's too hard.
That's the one I want to understand, but I'm trying to get
If
a
you want-
shortcut by looking at this last one.
If you understand this one, that's the main thing. Okay, so if I integrate by parts, we have the integral of u dv is equal to uv minus the integral v du. Yeah, that's what that is. That's all it is. It's just a way to integrate.
So by late thinking. So we are talking about not starting with one point, but with many points. So maybe starting tomorrow and working. We don't know what tomorrow is. Is that what's happening?
What's happening here is we're throwing away every sample path that might have crossed over the threshold and not counting. That's all.
We are looking at different starting points.
Yeah. And it is an option price. Yeah. These are my pictures. Okay, so I'm going to skip over these. I found a lot of analytical option pricing formulas, but I just want to talk a little bit about what it means. So I've been spending my life, my pencil and paper, finding option pricing formulas, but I think it has bigger implications than just me entertaining myself. There are new option pricing formulas can come this way because it's an automatic way of putting that kink into your calculations as option pricing people need. But one of the big things that people always want to know is when can I come out of lockdown? Gladys says, I don't know. But there is some probability of that, right? And one thing that we know almost nothing about is first passage times. What's the time that it's going to take me to reach this threshold? We talk about what temperature we're going to be getting too warm in the world, but we don't have the probability distribution for when that's going to be. But I think these, I call them threshold probabilities, could tell us about time as well as a random variable. So instead of y being a random variable, t becomes a random variable. And that's what people really want to know is when. But we don't know much about that. We know 2 first passage time probabilities, and that's it. But maybe we can find more. Econometrics. When we're doing econometrics, we're assuming stationarity. If we're doing adoption studies, we're using cumulative probability distributions. I'm saying that that's the wrong distribution to formulate likelihood out of. If you're doing adoption studies, you probably need to think about thresholds, which is a different thing. But let me skip down to what I really wanted to say today. Decisions under uncertainty, I think, come in 3 sizes: small, medium, and large. So small, we use the transition density, form our likelihoods, make our decisions using whatever your favorite thing is. I use stochastic optimal control or stochastic dynamic programming, but you make small decisions. Medium decisions, you use the probability, and I think that's where we use that one, the minimum one, the transition probability. It doesn't matter much if we cross this threshold, and it might be easy to come back. So we can do a cost-benefit analysis of 2 different alternatives with the idea that we can switch between them. That's no big deal. But I think for the large decisions where we're going to cross a threshold and we're not coming back, we need something else, and we need a new toolkit. So our toolkit is all about a nice concave world. Yeah, I do my marginal conditions, and then I got this nice concave profit function or utility function or something. I take the derivatives of it, and I get to the top of that nice concave hill. I get the best possible decision. What if my world is convex? And I take derivatives. I'm down here at the bottom. I don't get the best decision. I don't even get a good decision. I get the worst possible decision. Our marginal tools will give us the worst possible decision. So these economists who got up and said, we got to measure the marginal benefits of staying in this pandemic, lockdown, blah, blah, blah. They were telling us the worst possible things to do. Because the world of thresholds is convex. And I'm not the first one to say that the world is convex, but we need a new toolkit for these big decisions. Thank you.
I've been interrupting, so let's hear from the other room. Anyone thinking about that version of this? Two chance to figure out. There is another way, right?
Well, not for your thesis. Don't worry about this for your thesis. We're off the
Does
planet
this
here.
allow new variables, explanatory variables? Because we are looking at two things, like time and value.
Yeah. And I just think everything has time in it, right? Long ago gave up trying to analyze the decision without time in it. It's always been this way.
And most of our time we spend trying to explain things using other variables. So.
Yeah, yeah. Well, okay, in these probabilities, you can put in all kinds of other variables.
Yeah.
So I've got one where you put in all these nice deterministic time trends, and you can put in demographics, and you can put in all kinds of things.
Yeah.
For this purpose, those are just constants that don't alter anything. You can just stick them in. So all those other things you would. This is just, I mean, it's probabilities and thresholds. That makes sense?
Yeah.
Nothing we do is wrong. It's just I'm trying to get us to put time in.
Dynamics, yeah. That part of economics is sitting on the side all the time. Yeah, it's taught in some places, but when you come to the empirical side, it's hard. It's hard. So it's mostly people doing dynamic optimization, and that's a small part.
Yeah, yeah. And while the profession is going more towards applied econometrics, almost exclusively, and away from the theory stuff. Firmly in the I do econometrics. I love it. I'm one of those people who thinks you need a good theory and the econometrics, not just the econometrics. I teach in that all the time. I say that many times, but they all go out and do their thesis. The determinants of the adoption.
Any questions now? Okay.